Hi everyone, welcome to this episode of Kuiper Labs. In this video today we're going to be talking about the concept of gas pressure. Okay, so starting to think about how gases behave and some of the different properties that they have that aren't really relevant when we're thinking about liquids or solids, and how we can use our understanding and model of matter to be able to predict and explain what gases do. The first thing that I want you to try and think through is a scenario of a cup. I know, particularly outlandish for me to suggest such a thing. So a cup filled with water and a straw. And I want you to think and take some time to try and picture and imagine how a straw works. Take some time to pause the video now and see if you can think about how you are actually able to suck liquid up a straw. Okay, so hopefully you've taken a little bit of thinking time now. If you haven't, pause it and do it. Okay, do it because I'm asking you to. Alright, a little bit of thinking time here is important. Okay, but so we all know, we've had this experience where you put a straw into a drink and then, you know, even as a baby, that this is one of the first things that you learn to do, and then you suck, and then the water makes its way up the straw and into your mouth, and hey presto. And so, but what I want you to, one thing that might kind of blow your mind here is that there is no such thing as sucking up a straw. Now, I understand that that's a bit of a surprising sort of strange sort of thing for me to suggest. I was like, of course, Mr. Kuiper, there is sucking up a straw. I mean, we drink through a straw all the time. Okay, there is no such thing as sucking up a straw, believe it or not. Now, we all know that there is something that happens when you put a straw into your mouth. You're able to drink through it. So there is something that is going on here. But using this particular phrase is not helpful. Okay? I'll explain to you why. Okay. Let me see if I can redraw this a little bit, perhaps a little larger, to help visualize a little of what's going on here. Okay, so let's kind of imagine our cup here, nice and big. We've got a solution here, and then this is our straw. Okay, now we tend to think about sucking up something up through a straw in light of the fact that there's liquid in here. But the reality is that we know that the rest of the room is actually what makes the straw work. Because remember, so we have water here in a glass, but around here we have air. Okay, all around. That we say that it's pushing down on this water. Okay, and so it's exerting a force, helping to push down on that water. Okay, even though what we tend to think that force is fairly inconsequential, that it's kind of nothing, because we live our lives experiencing this very same force and don't really pay it any mind. But what's happening when we suck on a straw, or when we are using a straw? Okay, so you think about what's happening inside our mouth now. I mean, clearly I'm rubbish at drawing, so I'm not going to try and draw someone's mouth at the top of this straw, so we'll just bear with me. Okay, but so what's happening is that when you put your mouth over a straw and then it feels like you go to suck it in, what's happening is that there were some air particles that were in here before. Okay, so if this kind of represents the air particles that were inside that straw, okay, they make their way out of the straw, up the top. Okay, because, and actually it's what's happening with your diaphragm and all the muscles inside your body that are actually making that work, just quietly. Alright, but so what happens is that those air particles now aren't there anymore. Now, originally what happened was that the air that was inside the straw pushed down on the liquid that might have been in here. Okay, it pushed down on the liquid, and then to balance out what's happening that's pushing down on the rest of the water. But all of a sudden, if that air isn't there anymore, we have a force pushing down on this water that isn't balanced by a force pushing down up here. So what happens is the particles of water start to make their way up into the space in the straw, rising further and further up the straw until eventually it gets to our mouth. And then we have a drink in our mouth that we're able to swallow. Okay? And then in doing so, that we end up with the level of liquid decreases. Okay? And this keeps going until eventually we run out of liquid, or perhaps if we keep the straw there, the level of liquid gets below the end bit of the straw, and we can't get any more up there anymore because we've just got this air. Now, one thing that I really want to encourage you to try and work this out, we'll kind of observe how this is strange. I'm not going to tell you how this is going to turn out, but do try it at home. Okay? Is if we have some water in a container and you have two straws. Okay? One straw in and one straw out. Okay? And take a drink. I dare you. See what happens. Okay? And so what we're talking about here, this force that's pushing down on the water here, is this concept of pressure. Okay? We're talking specifically, we're talking about gases at the moment. So it's a pushing force. Okay? And so what we would say is that we say that pressure is a force, an amount of force divided by an area. Okay, this is one way that we can calculate it. We're going to talk at a particle kind of level in a second about what pressure is like, but we can say as, okay, well, it's a pushing force, okay, rather than a pulling force. So it's not a pull. Okay, so it's a pushing force that then is divided by the area over which it's applied. Okay, so the bigger the area, the less the pressure is. Okay, or the bigger the force for the same area, the bigger the pressure is. Okay, or if we take the same force and we apply it over in a very, very small area, we get a very high pressure. Okay, so this is, say, just to kind of give you an example, all right, it's perhaps a little gruesome, but if you take a lump of metal and then you push it against your skin, okay, you will feel a pushing force and your skin will kind of bend and then will bounce back. Okay, because it's applying a force over a certain area. Okay, now if you push really hard, okay, you'll probably break a bone or something, but just thinking kind of gentle pressure. However, if you take the exact same lump of metal and you change its shape so that it ends up being very thin and very narrow with a very small edge, and you do the same thing, such as in a knife, and then all of a sudden that pressure that amount of force over a very small area has a very high pressure and can pierce or puncture your skin. Okay, that's what something like a knife or a sword is designed to do. Okay, and so so this is a relationship that we can calculate. It's a relationship that we can measure, and it's also kind of a basis of a whole lot of other kind of physics principles like hydraulics. You know, like if you think about how like hydraulic lifts in lifting a car up, for example, is able to work. Okay, it kind of takes this sort of principle. Okay, but we're saying that it's a pushing force, but I want us to think about, okay, well, at a particle level, where does the force actually come from? Okay, because we know that matter is made up of small particles. Okay, and so what we're saying, and particularly when we're applying it to gases rather than liquids or solids, okay, is that we know that if we had a sample of a gas in a box, that it's made up of lots of small particles, okay, that are very far apart from each other. They've got no interaction with each other, aside from if they occasionally collide with each other. And they're all traveling. They have energy as a result of their motion, kinetic energy. Okay, the amount of kinetic energy relates to the temperature of the gas, but otherwise that these gas particles are moving in all directions. Okay, now, say if I take this little gas particle over here and I look at its current kind of direction that it's going in, okay, eventually it's going to hit this point in the container. Like a pool ball, it's going to hit here and then maybe it'll rebound off this way, or depends on the exact angle that it hits. Okay, but basically there is a pushing force here. As it collides with that container, it exerts a force on the container. And then if we take this one over here, this one's going to have a pushing force too. Okay, so for every collision, exerts a pushing force on the container. Okay, or we might generalize it out to think about on an object or any object, because the air exerts this same pushing force on us. You know, we don't think of ourselves as a container, but it's exerting this pushing force on us because of the collisions of the particles with it. So that means that if we have more particles in a given container, we get more collisions, and that means we get higher pressure. If I take a container and I pump more particles in, but I don't change the container itself, I will get a higher pressure inside. Okay, if I do it to something like a balloon, which is able to change its shape, then that higher pressure will then cause the balloon to expand out slightly. Okay, as I let particles out, then those particles can escape and the pressure decreases, and so the balloon decreases. Okay, so more particles in a box, in a container, gives us more collisions with the container, and therefore we get a higher pressure. Okay, so this idea that the pressure of a gas relates specifically to the collisions of the particles with the container, this pushing force. Okay, more particles gives us more collisions, therefore a higher pressure. Okay, thanks very much for watching. Now I'll just give you a chemistry joke to finish up. Okay, so Helium walks into a bar and goes up to the barman and asks for a beer. And the barman says, no, we don't serve your kind here. No. And Helium, he doesn't react. But see you next time. Bye for now.